Students. So, uh, this is the part where I talk about energy, and I want to be careful when I talk about it because um, the way we're going to talk about it is kind of unusual, and it brings up minus signs throughout every equation. So I just want to be careful about it. We're um, all right. We're going to talk about energy and um, how to deal with problems with it and how to uh, consider what's going on. So we're going to start unusually. We're just going to go straight into calculus. We're not going to try to justify anything. I'm just going to claim that, and other people have proven this, that if we have a force, then this force is going to be minus the derivative of a potential energy with respect to some distance. So, and so, hang on a second. Oh, okay, so somewhere else. I just heard the thing from the office hours, the chat window beep. Anyway, so the idea of this is, if you remember, our work was F dotted with delta x, which really is integral of F dr, where r is some displacement vector or set of displacement vectors you're adding up over. All right, so, but this work was really minus a change in potential energy. Right. So, I mean, it wasn't obvious that this is true because this is only true if it exists. Right? If there's, all right, friction wouldn't have a potential energy with it, but gravity does. And you can show that, because the work equals kinetic energy, right? So work equals change in kinetic energy. And then what we want to say is kinetic energy equals minus the potential energy. So that's K final minus K initial is U initial minus U final. And then we're going to group things all together. And so we get K final plus U final equals K initial plus U initial. But that's just energy final equals energy initial. All right, so starting from here and saying, the mechanical energy is the same, and then saying, well, it's kinetic plus potential, and then separating it out. The change in the kinetic energy would have to be the change in the potential energy. And this is not a conservation statement up here. We're saying that the change in kinetic energy is some internal force that does work that gives you a change in the potential energy. So when you drop an object, right, if you have, so you drop an object like this, then the Earth does work to move the object. And the Earth doing work to move the object means that you have a change in the potential energy, it drops, and a change in the kinetic energy, it goes up. All right. So we can always write something that looks like this. So let's do that in terms of gravity. We have on one side g, the mass of the big thing, the mass of the little thing over r squared is minus derivative of u over derivative of r. And so, by the way, these things I'm writing here that are not, like dr, dt, something like that. These are what's called partial derivatives. So what that means is you only take the derivative if you actually see the letter R somewhere. I mean, it's not a perfect description, but that's the gist of it is, you're not m here. The mass might depend on the radius, but you're not trying to get in there and get the functional dependence there. You just take the derivative directly with, you do it the easy way. And the reason you do that is you might have, this r might be x squared plus y squared here. And you just want to take the derivative with respect to x. You say y is constant. So all other terms are constant. But as it matters, so, that's just a notational thing, and it's habit. So just be aware that this is just derivative, and it's just, if you want to, just view it as me being sloppy until it matters. So what is a formula that if I take a derivative of it, I get this? Well, it's got to have these masses and g here because those are constants. And so we're looking for g, big mass, little mass, times r squared is g, big mass, little mass, times derivative of something with respect to r. So what thing, sorry, there's a minus sign here. What thing, when I take the derivative of it, I get effectively minus r, 1 over r squared. Now that's 1 over r. Derivative of 1 over r is minus 1 over r squared. All right, it's r to the minus 1, d by dr, is minus 1 r to the minus 2. And that's minus 1 over r squared. So what this means is, right, for a force that looks like g mass 1 mass 2 over r squared, our energy, our gravitational energy, looks like minus g mass 1 mass 2 over r. All right, because if you take the derivative of this with respect to r, you'll get this. Okay, and note that there's a minus sign here. There's a reason for that minus sign to exist there, and it's not just because of this. All right, but that's certainly why we're doing it now. So that means we can go and write the mechanical energy, and I want to write that out now. So we're going to do this for something that is orbiting a planet like this. So this thing has little mass m, and this thing has big mass m. And so this thing has kinetic energy. And so we can write that the mechanical energy is, well, it's the kinetic energy, so it's 1/2 mv squared plus the potential energy, but the potential energy is minus g big mass, little mass over r. And so we'll put in a radius r in here. And a velocity v. And you could do things like take this v squared, and since this thing is moving in a circle, right, you would have the orbital velocity, right, is gm over r square root. So you could put that in, and it would be g big mass, little mass over radius. And so effectively you have plus 1/2 of this term, so it's minus g big mass, little mass over 2r. But we don't really want to use that. we want to look at this expression here, because we can ask some questions. Like, let's say this is the Earth and this is us. And we look around, you know, we look around the Earth and we make what I think is the reasonable idea is that we want to go not here, but there. We want to go as far away from the Earth as we can. How do we deal with it? All right. How do we get to the other side of the room? Basically, infinity away. So, well, let's look at another case. All right. So let me draw. Here's the Earth. Here's our spaceship. All right. So as we go further and further out, what is the potential energy going to look like? Well, it looks like this term, minus g, big mass, little mass over r. As r increases, this term decreases. So we can plot u and r, and it's just a 1 over r function. So as you approach infinity, u goes to 0 as r goes to infinity. Right. So I kind of want to go back a couple pieces of paper here for a moment. When I made a statement like this and like this, remember that these are all definite integrals whenever we do them. They're not hand wavy indefinite integrals. We're trying to do actual integrals. And so we can come up with this and say, when we're trying to do an integral to figure out something involving this work or this potential energy, we need to find some place where the potential energy is 0. And we're going to say that it's going to be at r equals infinity, 0. And so what happens is when we do some sort of integral like this, one of our things is going to be infinity. But when we plug infinity in, it's going to be on the bottom of our integral. Right? It's going to be 1 over r. So we're going to have a 0 there, and that's going to be good. So we want our little spaceship to go as far away as we can. And we've already said that energy has to be conserved. And we've wrote the mechanical energy, and we even calculated what it might look like just as a total. If this approaches 0, this has to approach the total mechanical energy. Or I should say it a different way. If this goes to 0, it's growing because it's negative. It starts as a big negative number and goes down to 0. So this has to decrease. And so what happens is, to get away from the planet, you have to slow down. You have to trade kinetic energy that you have here for potential energy far away. And so what we would do is set up the problem, right? We'd have energy final equals energy initial. Well, our energy initial is going to be 1/2 mv initial squared plus g big mass, little mass over the radius initially. And then on the other side, we have 1/2 mv final squared. Oh, and I should put in the obvious minus sign that should be here. So, and then we'll have minus g big mass, little mass over r final. But r final is infinity, which means this term goes to 0. So we're left with an equation that looks like this. And now we want to set a minimum. We want to say, what is the minimum initial velocity we have to escape? So it means Vf is, when we get to infinity, V final will be 0. So we'll have 0 is 1/2 m v escape squared minus g m1, big mass, little mass over the radius. And then we rearrange this. Note the little masses go away. It doesn't matter what your mass is, it matters the thing you're trying to escape, the planet. And you eventually calculate that v escape is square root 2gm over r, which seems familiar. Our orbital velocity was gm over r. So your escape velocity is about 1.4 times your orbital velocity. Right. So you can use this equation a couple of different ways. If you're in a particular location with some radius r that you're orbiting around, how much speed do you need to get away? You can instead say, I have this speed, where can I escape from? So we want to figure out the escape velocity. Let's say we're doing this from orbit, right? So we have something to compare about. So when we had the previous video and we're trying to find the orbital speed, it was 7.6 kilometers a second. And the way I said it was, this square root of 2 is what matters. 7.6 times square root of 2. We're looking for a number that's about 10.7 when we calculated it out. So we want to figure out the escape velocity for the Earth at, while we're in orbit. And we can do that, and I'll sketch it out right up over here. Is the escape is 2 times 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times 6 times 10 to the 24 kilograms. And we're going to divide by our radius here is 6.8 times 10 to the 6 meters. And then we're going to do that to the 1/2 power. And so V escape is going to be 2 times 6.67, clear, 2 times 6.67 times 10 to the 11 minus 11 times 6 times 10 to the 24 divided by 6.8 times 10 to the 6. Square root that, and we get 10.849 or 10,849 meters per second, which is about 10.8 kilometers per second. The number we usually quote escaping from the ground is about 11 kilometers a second. So that's the thing about launching rockets off of the Earth. We might have talked about this a little bit in momentum, about the rocket equation. It's certainly in the textbook. But to escape from the Earth, almost all of the energy is to put you in orbit, to go that 7 kilometers a second. And then just a little bit extra is needed, is 1.4 times as much energy is needed to escape. Right? So, you don't need that much change in velocity to escape the Earth out. You could also calculate, well, what if we want to go stand on the surface of the sun? That means you got to change R here to the size of the sun. And that means you got to slow down a lot more. Okay. So when you're talking about the actual motion of like spacecraft in space, you're dealing with the fact that you have a bunch of motions going on. The Earth is moving, you're moving, the sun is moving, other planets are moving. And you have to calculate velocities and distances appropriately relative to the thing you're trying to deal with. So let me also take the moment while I'm doing this video and I'm 20 minutes in. Let's talk about black holes. The whole thing with black holes is that you can't see them. And that's a classical phenomenon. We can look at the escape velocity as the speed of light. If you have to go faster than the speed of light, you can't go. You can't see it. The light can't escape. So stuff happens and the light just never gets to you. So we're setting the escape velocity is to c, but that has to be square root 2gm over r. Now we're going to revert to problem and say, how far away from a mass do you have to be to not be able to escape it? And so, square both sides, and then we'll have r is 2gm over c squared. And we'll put a little subscript s here. This is what's called the Schwarzschild radius. Scientist, German, I think, obviously from the name is Schwarzschild, deduced from not just this, but from relativity, that you would have objects where inside of this radius you can't escape from, and you can't see these objects because the light can't escape from inside that radius. So, that's now the unusual bit is, you have these what I would call classical black holes. Is the idea is that light can't escape from them, but for most normal objects, all right, if you calculate this radius for the Earth, all right, we can do that. It's 2 times 6.67 times 10 to the 11 negative times 6 times 10 to the 24 divided by 3 times 10 to the 8 squared. It's on the order of a centimeter. You have to be a centimeter away from all of the mass at the center of mass. And that's what's wrong, is the mass isn't concentrated enough in the case of the Earth. But black holes are really weird and unusual, and really a topic for the astronomy class and for the relativity chapter when we get there. So we're going to kind of let this walk away and end the video here. We do have more to do, but the gist of this stuff is, when we're trying to solve problems in energy, it's just an energy problem. We're not going to try to come up with any new stuff. We have this new term for our gravitational energy, and we're going to use it to calculate mechanical energies in different places. And that's why I went through and talked about calculating the escape velocity. That's what we're doing. The energy on one side has to equal the energy on the other side, and we get this stuff. So we'll pause the video there, and the next one should be Kepler's laws, which should be reasonably good.